So this is the third day of solving first order differential equations. In day one, we talked about separable differential equations, and we said, separate the variables, life is good. Day two, we talked about what we call linear first order, and in that case, we said, if you choose the right thing to multiply by, choose wisely, then you can make the left-hand side of an equation, the parts that involve the y, look like a derivative. Then it's easy to integrate a derivative, and life is good. So now we come to the third day. And in essence, we're going to mostly finish up what we can do with first order equations today. Now, I don't want to say that we'll be able to solve every first order equation you ever see for the rest of your life. Not even close. But we can solve the ones that we can reasonably ask you to solve. So that's the goal. So what's today? So today we have something called exact ODE. So remember, ODE is short for ordinary differential equation. It's really hard to write that so it fits in the line. So we abbreviate. And what does that mean? Well, it's something that you can write in the form some function m which depends on both x and y. It's an expression. Dx plus some function n that depends on x and y, dy equals 0, with a little bit extra. So it's not just any arbitrary m and n. They have to have a nice property. So this is for all you Calc 3 lovers. And I know you're in here, you lovers of Calc. I should just say calculus lovers. You'll see that there's sort of like, it's like, Steve, you wrote the D symbol wrong. That looks like it's sort of been out in the sun too long and it's starting to wilt. But no. This actually means partial derivative. It's just a fancy way of saying this function here depends on two different variables, x and y. But we're only going to take the derivative of just the parts which involve y. We'll treat x like a constant. So that's what we mean when we say partial derivative. So take the partial derivative of this first part, m with respect to y. If that equals the partial derivative of this second part, n with respect to x, you're exact. Now, what's nice about exact functions? Well, if you took Calculus 3, it turns out that one of the things we talk about, it says if something's exact, if it has these lovely properties, then what happened is there's actually this function f of xy equals an arbitrary constant that it came from. In the following sense, that this m is the partial f of partial x, and this n is partial f partial y. And if you don't like multivariable calculus, you can also think of single variable calculus and say, well, it's implicit differentiation of this expression f of xy equals c. So that's all right. So there's this fact that there is some solution out there. So our goal is, how do we find this function f xy? So that's the goal. So we have to find that. Now, there's a phrase for it. It's called the potential function. And, well, the way we do it is we build up using our m and our n. And there's a couple of different ways to do it. But you know what? Let's just cut to the chase. This is what I think is sort of the simplest way. So 3 steps, right? How hard could it be? Well, take the quiz next week and you'll find out. Oh, good times. Okay, anyways. All right. So step 1. See, the idea here is if we're exact, so step 1 says, hey, this part right here, we're going to think of this m as partial f partial x. And we say, I have a derivative of the function. If I have a derivative of the function, all I have to do to get the function is to do what? Is to integrate. If I have the derivative, I just integrate, and life is good. So it turns out that if I integrate the part attached to the dx with respect to x, I have the function. Well, not quite, right? When you integrate, what are you off by? You're off by a constant. But now here's the fun part about multivariable calculus. The constant might not be a number. It could be anything that's constant with respect to what you integrated. So we integrated with respect to x, so y is now a constant. So it turns out that this piece right here, if you add a constant function of y, so not a constant number, a constant function. So we don't know what this function of y is, but this is, in fact, f of x comma y. And now we say, okay, well, wait, same idea. If it's exact, this piece right here, that's partial f, partial y. And so we repeat the process and say, oh, integrate that part with respect to y. So this is also f of x comma y, but now since you're integrating with respect to y, your constant is not a function of y, it's a function of x. And so what you have is you have two different ways to express your function. And now you check. So this is our check. Because not everything is exact. So here's where we find out if it is. So how do you check? Well, you say, okay, look at your two different integrals, and you ask yourself, what happens with the terms that involve both x and y? So I don't care about terms that only involve x, and I don't care about terms that only involve y. I care about terms that involve both of them. They have to match. Now, I'm going to be really careful here for a mysterious reason. I'm using a word here, equivalent, which means they have to match up to possible rewriting. Occasionally, of course, who doesn't love a good trig identity? But the point is, you cannot rewrite one to get the other. Then it's not exact. But if you can rewrite one to get the other, it is exact. So that's your check. So if it's not exact, you stop and you just say, all right, got to go try something else. If it does match, then we say, okay, we know our answer. It's going to be f of xy equals c. And we say, all right, I have to form the f of xy part. There are three things. There's the common terms. So the common terms, that's what you found in step 2. Things that involve both x and y. You add that to f of xy. And now you say, okay, what about things which only depend on x? For things that only depend on x, you go to the integral where you integrate with respect to x and grab those terms. For the things that only depend on y, whoops, there we go. You go to the integral where you integrate with respect to y, and you grab those terms. And so you have three parts. What's common to both, what only has x coming from the integral of m, what only has y coming from the integral of n. Throw it all together, set it equal to an arbitrary constant, and you're done. That's it. That's the whole procedure. Okay, that's the theory. Are you ready for the practice? Let's try it. Okay. So, I guess I should have said one more thing about this. There's always the question, how do you know when you should try to do an exact ODE? Like, if you look at a problem, you always ask, what's the right technique? So, here's generally my interpretation of when you should apply an exact ODE. So, well, this is not an exhaustive thing, but here's if it looks hopeless, try exact. So in other words, it looks really messy and complicated, and there's lots of stuff floating around. The more flotsam and jottsam you have, the more it's like, that's probably exact. So we make things look complicated deliberately to send you a signal. This is exact without actually saying the words. So anyways, so the more hopeless it looks, the more likely it's exact. Okay, so, all right. With that out of the way, our first example. Okay, so solve 2xy squared plus 3x squared dx plus 2x squared y plus 4y cubed dy. Now, this doesn't look terribly hopeless, but it'd look messy if we tried to do it with tools we have, in that we can't separate it, and it's not linear first order. So yeah, we'll do exact. We're kind of hopeless if it's not those two. So, all right. So, what's the key? Now, in our case, it already started as dx and dy. Suppose they had written the following: something something dx plus something something y prime. What would you do? Yeah, replace y prime by dy dx and multiply through, so you can have something times dx plus something times dy. Now, the nice thing is these problems work themselves. You say, okay, I see something with the dx here. Integrate that with respect to x. Okay, so let's integrate it. Integral of 2xy squared with respect to x. So remember here, treat y like a number. The only thing that's changing is x. So integral of 2xy squared would be x squared y squared. Remember, we're integrating. So y squared is like 5, so it's like 5 times 2x. Integral of 2x would be x squared. Integral of 3x squared with respect to x. X cubed, right? Because you add 1. Now, what else will there be? Just because we want to be, yeah, plus something constant with respect to x, a function of y. Okay, now we say, and look, there's this other part attached to the dy. So we're going to integrate that with respect to y. See, isn't that so intuitive? What's attached to the dx? Integrate with respect to x. What's attached to dy? Integrate with respect to y. Couldn't get nicer. Okay, so we have to switch our minds here, right? We used to think of x was our changing thing, y was constant. Now it's vice versa. Y is our changing thing, our variable. X is our constant. So the integral of 2x squared y with respect to y. X squared, y squared. Integral of 4y cubed with respect to y. Y to the fourth. And then something that depends on x. Okay, so we finished our step 1. We took our two parts, we integrated them. Now we're into our check phase. So, in the first term, which of these parts involves both x and y? Yeah, the x squared, y squared. Anything that's separated by a plus, we treat them as like separate blocks. How about in the bottom part? X squared, y squared. We say, okay, now we have to compare these two. And we say, are these equal? And they are, so that's good. So that means that we are exact. Well, we kind of knew it was. Now we're ready to put our answer down. So our f of xy, well, you take the parts that match. So that's x squared, y squared. And now you say, okay, good. I go to the integral with respect to x, and I grab anything which only has an x in it. What do we grab? X cubed. So we have an x cubed. And then we go to the part where we integrate with respect to y, and we grab anything that only has a y in it. What do we grab? Y to the fourth. And then we set this equal to c, and I'm trying to be way too colorful here, because there needs to be a constant somewhere, so just throw the constant on the other side. So the point here is this is our function f of xy in our various parts. What they have in common, the part only dependent on x, the part only dependent on y, and we're done. If they gave us an initial condition, what would happen? For an initial condition, you just plug in, what they'll give you is they'll give you a point. And you just plug x and y into here, and you get what c needs to be. Okay, one more quick note, and then we'll say that this problem is good. If you look on we know that these parts match. Do these parts match? Well, the answer is, they actually, if you think about it, that x cubed is hiding in the d of x term. That y to the fourth is hiding in the c of y term. That's why you have to do both integrals. Because if you only do one, you can't capture what's inside that function. So collectively, these are equal up to whatever, knowing what's inside those functions. So, okay. All right. Good. Any questions?
Yes.
Yes.
So if that was written in y prime, the dy was written as y prime, so you're going to have dy over dx.
Right.
You said multiply through by dx.
Right.
How does that affect the very first term? Does that give you a dx squared?
Well, no. It would be written in the following way. It would be 2xy squared plus 3x squared plus, they might not even put parentheses, those punks. Trying to make it hard on us. So if you have this, then what you do is you think, oh, replace this y prime by dy dx, and then multiply by dx. So then this would become just dy, and then this term would attach to dx.
Okay, so you would never have a situation where you might have a y prime at the end and a dx?
No.
Okay.
Now you shouldn't. Mistakes were made. But no, we would never give that to you, because we only give you the good notation. Fingers crossed. Other questions? Yes?
So this constant, like constant with the y,
Constant y?
include the like normal constant too?
Yeah, this could include some arbitrary constant that we don't know about. So that there's an arbitrary constant here as well, and that's reflected in the C. Yeah, so we don't know what the arbitrary constant is. We would need an initial condition to find it. Solve. Now, see when I said hopeless? That looks hopeless. But x plus arctangent of y plus x plus y over 1 plus y squared y prime equals 0. Okay, so this gets back to, we have a y prime here. So we mentioned this a little while ago. You say, you make this dy dx, and you multiply through by the dx. Now another thing, by the way, is you really want to make sure everything's on one side. So if you have some stuff on the other side, bring it over. If you're planning to use exact, make sure it's all on the same side. Okay, so x plus arctangent of y dx plus, and here we can really think of this as x over 1 plus y squared plus y over 1 plus y squared dy. So this is using the fancy fact that you have an addition upstairs. Addition upstairs lets you separate. All right, well, now we go through and do the integral. So this first integral, there's a dx, integrate with respect to x. So it's x plus arctangent y dx. Well, all right, I know the integral of x. Okay, half x squared. Integral of arctangent. There's like, I guess there's like a way to do it by parts, or wait, how do you integrate arctangent y? It's a constant, because we're integrating with respect to x. So it's a constant. Oh, that makes life so much nicer. Woo! Phew, dodged a bullet there. Okay, plus some constant function which depends on y. All right, we go to our other one. We're integrating x over 1 plus y squared, y over 1 plus y squared, dy. Okay, so x is like a constant, so you can think of pulling it out. Integral of 1 over 1 plus y squared is arctangent. It's oldie but a goodie. And for y over 1 plus y squared, what do? Use u substitution. U is the denominator, du would be 2y dy, so you're off by 2, so that's where you get a factor of a half. Natural log 1 plus y squared, or we can say y squared plus 1, and then plus something that depends only on x. And now we go through and do our check. We say, well, this has both x and y, and this has both x and y, and they are the same, so life is good. Means we can solve it. X arctangent y. We come up and say, okay, there's an x term, got to throw that in. There's a y term, got to throw that in. And we're not done until we set it equal to a constant c. Nice. Cool. And that's it. That's the process. So I should make one comment and put a little star here. The answers you get off of this are often going to be implicit functions. So unless we explicitly ask you to solve for x or solve for y, just leave it in this format. Are there any other questions about this? All right. Well, that's the first part of the lecture, which is good because that took half of our time. And now the real part of our lecture, our part 2, which is substitution. Now, substitution, you might think of like, well, I learned something called substitution when I learned integration. And it's basically the same idea. We're just going to introduce a new name. So what's substitution doing? Why do we use substitution when we do integration? The goal of substitution is to simplify the expression you're trying to integrate. And the reason we try to simplify is when it comes to integration, there's 10 things we can integrate. And if you're not on that list of 10, forget it. It's hopeless. And so everything is saying, how can I make it look like one of the 10 things I can integrate? So that's why we use substitution, is to help simplify and get something that has a better shot. So what do you do? Well, the thing is, there's never like one substitution. There's many different substitutions that can be done. So we're going to go through and look at a few of the classics. Now, in the interest of time, we're only going to get to the point where we do the substitution, update the differential equation, but we won't solve it unless we have lots of time, and then we'll come back at the end and start solving some of these. So, what's something you might see? Well, there's this notion of like a linear substitution. And so, suppose you have ax plus by plus c showing up inside of functions. In fact, you'll often see this notion of inside of things. If you ever think about substitution for integration, you often think about, oh, look for the inside function. And it says, okay, you introduce a new variable, and you have z. And you say z is the part on the inside, ax plus by plus c. And then well, all right, what's the goal? Well, the goal is, if you make a substitution, you have to update everything. So what we're trying to do is we're trying to swap out what's the derivative of. So here, y is what we're taking the derivative of. So if I have z equals ax plus by plus c, I also need to somehow replace y prime. So, well, you take z prime, and you think of taking the derivative with respect to x. All right, a plus by prime, and solve for y prime. All right, that's the idea. Let's see what happens. So suppose we come over here. What's a substitution we could make? Yeah. The part on the inside is a great candidate. So we're going to make this substitution. We're going to let z equals 4x plus y plus 3. So now the point is, we're going to make a differential equation, which is the ODE, in terms of z. That's where we're going. That's our goal. So I can't just replace this part. I also have to replace the y prime. Remember, in substitution, you have to update everything. So it's not just the function. You also have to do that, update the dx or the dy or whatever it is that you're doing. So we say, okay, take the derivative, z prime. What's the derivative of 4x? 4. What's the derivative of y? Y prime. What's the derivative of plus 3? 0. So we say, look, that says that y prime is z prime minus 4. So now we can update. So our new ODE becomes what? Well, it becomes y prime gets replaced by z prime minus 4. And over on the other side, it becomes z squared. Or if you like, z prime is equal to z squared plus 4. Now, quick question. What technique would you use to solve this differential equation? Is it separable, first order, or exact? You have a 1 in 3 chance. Now you have a 1 in 2 chance. Separable. This is separable. Now you're probably like, well, exact, it doesn't look hopeless, so it's probably not exact. Why is it not linear? Well, because it's a square, z squared. So to be linear, you have to have a z and a z prime, and that's it. You can't have anything else. But it is separable because you can move the z squared plus 4 dividing. You can separate out the variables and go from there. Okay, so that's how you would do that. All right, well, that's one example, but we have more. All right, another class. A differential equation is homogeneous if it can be written in the form some function of y over x. Now, here sounds like a very big word, but the first part means same, and the second part, which sounds like genius, so it must be really smart, really you should think of it as sort of degree, roughly speaking. So like if you think of a degree of a polynomial, so x squared y cubed, for x y to the fourth, these would have, think of it as the total. So what's the power if you combine the powers of x and y? 5. You add 2 plus 3. Here, 5. So this would be something that's homogeneous if you added these together because you have the same degree. So that's what that is coming from. So suppose we have y prime equals f of y over x. Then they say, aha, see how this y over x is the part on the inside? So we'll make a substitution. Z equals y over x. And you say, all right, well, that's great. So you do that. Z equals y over x. And then it says, well, to take a derivative, quotient rule is hard. So multiply across, and then you can just do a product rule. So you get y prime. You take the derivative of the first times the second. That's where the z comes from. Plus the first times the derivative of the second. That's where the z prime comes from. So if you look at the equation, y prime equals capital F of y over x, this becomes, making the substitution, z plus x z prime is equal to capital F of z. So I'm just making the substitutions. Replace what's y prime, replace y over x. Now, question. What type of differential equation is this?
Separable.
It's separable. Now you might say, wait, hold on, Steve. You got us last time. But I see a z prime and I see a z. But you also have all this other stuff that depends on z. And that can be messy. You don't know what it is. And probably it's not pleasant. But notice you have, this is the same as x z prime equals f of z minus z. And now you say, oh, I can divide the f of z minus z across, I can divide the x across, and I can separate everything. Life is good. So this turns it into a separable problem. Except I think I misspelled separable there.
No.
Well, I definitely misspelled it on one of my 2 slides because I spelled it differently on the last slide. So I'll claim that was an A the whole time. All right. Okay, so example. X minus y times y prime equals x plus y. So the claim is this is homogeneous. And the thing is, you look at every single term. Don't worry about the y prime. You have to the first, to the first, to the first, to the first. Everything's to the first power. They all have the same degree. Life is good. So, what would you do? Well, if you think something is homogeneous, you have to write everything in terms of y over x. How can I make things look like y over x? Divided by x. Or, if you like, you can multiply by 1 over x. So x times 1 over x, 1. Y times 1 over x, y over x. Y prime equals 1 plus y over x. Okay, so now we say, haha, everything where we have our variables shows up in this nice way. So that will be our substitution to make. So we introduce, we'll call it z. By the way, you don't have to choose z, just choose a nice pleasant letter. Z equals y over x. And I don't memorize, like, oh, if I make this substitution, this is y prime. I just rederive it. The trick is not so much like once you have the substitution, how do you figure out the y prime? It's trying to figure out the right substitution. Whoops. Okay. Y equals xz. So y prime, derivative of the first times the second, plus the first times the derivative of the second. So in our case, we'd end up with 1 minus z, that's 1 minus y over x, times z plus x z prime is equal to 1 plus z. And this is separable. It doesn't look like it right away, but it is separable. There's a couple of steps you'd have to do. You would divide by 1 minus z. So you get z plus x z prime is 1 plus z over 1 minus z. Then you can subtract the z, so you get x z prime is 1 plus z over 1 minus z minus z. And then you say, okay, I have only z here. You divide that across, move the x across, you're separable, and off you go. Off to the races. But like I said, only if we have time will we come back and try these. Okay. So, Bernoulli equation. Now, what? Come on. I was going to say this looks intimidating, but it's actually like, oh, why did he get his name attached? This seems obvious. Well, because he was the first person to say an obvious thing, I guess. So a Bernoulli equation is a differential equation which can be written in the form y prime plus p of xy equals q of xy to the n. Now, if there wasn't a y to the n, what would that be? It would be linear. And we'd use our integrating factors, and life is good. So it's like, darn that y to the n. Why did that have to be there? But here's the idea. What you do is you say, okay, divide everything by y to the n. So this is what's been happening. Everything got divided by y to the n. So that's the first step. And you might say, okay, now what you do is this part right here, y to the power minus n plus 1. And it sounds more complicated than it is. When you actually go through the process, you're like, oh, okay, that's what it is. That's your substitution. And that's all you need to know. Everything else works itself out. That's all Bernoulli did. All Bernoulli did is said, oh, make that substitution. He divided and made a substitution. So that's all you have to do. All right, well, what happens? Well, of course, you can take a derivative. So z prime minus n plus 1 comes down. You subtract 1 from the exponent, so that's why you get y to the minus n times y prime. And then the great aha, this part matches there. So that matches up to a constant. And so you end up with 1 over 1 minus n z prime plus p of x z prime equals q of x. And of course, I was going to ask, what kind of differential equation is it? Okay, I'll ask. What kind of differential equation is it? Linear. The clue is it says it right there. So this is sort of like, most of the time when you make a substitution, a lot of times it comes out separable. But once in a while, the gods smile on us and they say, we'll throw you a linear. Okay. So here's a quick example. We'll just update this. xy prime plus 6y equals 3xy to the 4/3. So, first off, is it Bernoulli?
Yes.
Yeah. If you covered up that y to the 4/3, it's linear. So Bernoulli basically says, it's just that extra power of y that ruins it from being linear. Say, okay, step 1, divide by y to the 4/3. That's what I like to do. If I take y divided by y to the 4/3, let me write this as x y to the minus 4/3 y prime plus 6y to what power? Y to the negative 1/3 equals 3x. So we move that power of y across. And we don't have to think about our substitution. We say it's this part. This is our substitution. Okay, so given that z is y to the minus 1/3, what is z prime? Minus 1/3 comes down y to the minus 4/3, and then chain rule, y prime. Because we're taking the derivative with respect to x. Everything's a function of x, so like dy dx. So x is the function in the background for everything. And we say, oh, well, isn't that rather convenient that this y to the minus 4/3 y prime matches? And so, okay, so the minus 1/3 goes across. So we have minus 3z prime equals y to the minus 4/3 y prime. And now we carry out the substitution. So minus 3xz prime plus 6z equals 3x. And off we go. What would be the next step, by the way, for this problem? We're not going to do it all the way, but what would be the next step? We want to make what's in front of the z prime should be what? 1. So what should you do? Yeah, everything needs to be divided by 1 over minus 3x. So you'd end up with z prime minus, here it'd be 2 over x, times z is equal to minus 1. And the process continues, but we're not going to because we have other things. So many substitutions. So many. All right. Now, wall of text here, but the punchline is sometimes you have a second order differential equation which you can change. Instead of thinking about a second order differential equation, you can do 2 first order equations in a row. So you can reduce the difficulty to a first order, do that once, and then after you've done that, you have a second first order to solve. And it's by various substitutions. So there's 2 possibilities where you might encounter something. So the first thing that could happen, no y term. So your derivatives, there's no y. Okay, so what should that do? Well, you say, hey, since there's no y, we're just going to skip it and say z equals y prime. If z equals y prime equals y double prime, right? Because the derivative of z would be the derivative of y prime, which is y double prime. All right, so an example. Notice this first one. What does it have? No y. There's a y prime, there's a y double prime, but there's no y. So we say, great. For here, we make the substitution. Y prime equals z. Y double prime equals z prime. And then we end up with x squared z prime plus 3x times z equals 2. And what kind of differential equation is this? It's linear. So this one, you have a challenge separating it because of that 2. If there wasn't the 2 there, you could get away with it. We would have gone away with the 2 if it weren't for that little dog. All right. Okay. The other one is there's no x. So it's just y's and y primes and y double primes. Now this one is the interesting one. The counterintuitive one. So you're like, okay, so what makes it counterintuitive? Well, we're going to set z equal y prime. And you're like, wow, Steve, that seems so obvious. But it's slightly different than what we did before. Now, why do I say that? I kind of hid something. I swept some details under the rug. You see, when we said z equals y prime up here, we really were z of x equals y prime of x. Now down here, what we're going to do, you actually can see it there, which is z of y equals y prime of x. So there's this function here. It makes it slightly different. Now, how does it make it different? Well, now, take the derivative. So you're like, well, hey, no problem. Derivative of y prime, y double prime, life is good. What's the derivative of z? Well, but what's the derivative of the left-hand side? You want to say z prime, right? Yeah, because that's part of it. Is that all of it? And why not? Chain rule, yes. So think of taking the derivative here. Z prime, then you keep the inside the same, times the derivative of the inside. What's the derivative of the inside? Y prime. But what are we calling y prime? Z. So this is where there's this fun little wrinkle. So y double prime equals z, z prime. All right, well, let's try here. No x. So, again, follow the procedure. Z of y equals y prime. We get z, z prime equals y double prime. So, y will become what? It'll stay y. We don't have anything to do with that. Y double prime, z, z prime. Equals, over here, 3 y prime squared z squared, because y prime is z. Now, what would you do to solve this one? Divide by z. Okay, so you get y z prime equals 3z. What kind of equation is this? This is separable. You can separate the variables. And so, for instance, you would say z prime over z is 3 over y. Or you write this as dz over z is equal to 3 over y dy. Integrate both sides. Integral of dz over z, natural log z, equals, over here, 3 natural log y plus c. Now, take both sides exponential function, and you'll have z equals, can you see this? Y cubed, but what about the plus c? What does it do? Some constant y cubed. But z prime is y prime. So now you have y prime equals cy cubed. What kind of equation is this? It's also separable, and you can solve it now. So notice we started with a second order, got down to a new first order. We can solve that. All right, that's it.